I'm going to take a moment and just sort of press a reset button on what we've been learning about the iterated, or in our case, the double integration, the meaning of it, the notation of it. And so this is going to be brief, but I just want to run through what we've got so far. So there are some notations, and we've been playing with two distinct notations called orders of integration, where we could integrate with respect to y first and then integrate with respect to x later, or integrate with respect to x first and then integrate with respect to y at the end. And the ability to interchange between these two means that what we have is a region of integration, denoted by this capital R, has to be the same region. So long as the information here sets up into some sort of a visual where, let's say it's this, and let's say it's that, and this is our region of integration. If there is a way to describe this in either of these orders, so long as these setups represent the same region, then you will get the same value no matter what happens. Next, the function inside, if this z equals f of xy is positive, we could think of this as somewhat of a volume calculation. And what we have here is like the foundation of our building, and then we have the building that sits over the top of this foundation. And the building could have different altitudes and it can have an interesting roof on it. Volume is just one of the possibilities. So there's this generic notation, or just sort of a general notation that's used. The region, in this case, is two-dimensional. That notation here is to put a dA at the end. And you want to guess what the capital A is for? That's right. That would be area. So we think of our region, we have area, and if you think of area measured in square or rectangular units, base times height or height times base would be the way to measure that area. That's our loose interpretation. Again, you can get much more formal when you're reading through the books, which you should be doing. I'm just trying to put a spin on it to shed some light on it differently than the textbook can. Next, there will be another notation that we get when we convert from x and y to a different coordinate system. We'll have a different looking notation here, but it'll still have a double integral, and it still needs to represent the same region to make sense. And that's in section 14.3 in our book, and it's not for this video yet. We still have a couple more videos to go. All right, so some key items. The outside integral, which for us, let me just sort of point to the one I have visible here. This integration symbol right here has to be constants or numerical values. The last thing we do has to be to substitute numbers in. We need to get a number as an answer. These have to be constants, the last thing. I cannot stress that enough. That's the first order of business. Second, just a reminder that we need that region of integration to look exactly the same in order to switch. Okay, so just make sure what I've said about the region of integration, you can fill in that blank yourself there. Take your own good notes. Finally, let me just leave you with a couple challenge problems that I'm going to have solutions posted in Canvas after this particular module of videos. We're going to practice switching the order. And let me just see if I can't, a little switcheroo here. First integration, x goes from 0 to 1, and y goes from x squared to x. Trust me, that's lower and that is higher. Some generic f of xy function, so we can't integrate yet. dy dx, we're going to convert it to a dx dy case. And then finally this one, from -4 to +4, from 0 to square root of 16 minus y squared. And I just want to point out, since that says x, then that makes these x boundaries, and that makes these y boundaries. And you're going to switch this one back to what I'll call our native language, where we do y first and then x last. I will have the solution to this posted in the next item after this particular page in modules. All right, that's good. See you later.